If we now go to the stiffener buckling, we can take into account this effect with assuming that a stiffener plus a plate behaves as a beam. So if I have something like this with a stiffener in the middle, then I assume that my plate plus my stiffener combined, that forms some kind of a beam with an eye. And then I can calculate whether it buckles or not. And we take for the, well, different standards of course have different limits. The DNV, for example, also takes into account the effect of what happens if we have a side compression load, if we have lateral out of plane buckling limits. But again, I think that is details. The idea is if we take the width of the plate, so if we have a stiffener here and we have a stiffener there, and we take the plate and the, so for the plate we take, for this plate we take that so the effective width of this beam, we divide that over half of the plate goes effectively in the moment of inertia of this stiffener plus plate, and then the other one here goes into this stiffener plus plate. So basically what I do, I take into account that the plate width is up to the yield limit is it can be a you can form a kind of a beam element where you take into where you can take the blade effect, you can add it to the stiffen up till this effective width limit. This is for my students. If you want to design, if you want to figure out, okay, if I want to do a beam, if I have some kind of a beam and I want to calculate how many stiffeners do I need, I can now use this curve in the opposite direction, because now I have suppose I have a maximum stress in my plate, in my beam. I can then use this curve. Okay, what is my maximum stress? And then depending on the material I have, I directly have a slenderness ratio, which is allowable in my curve. And with this slenderness ratio, I can then define the length to width ratio directly. So if I say, okay, I have a maximum limit of 120, then the corresponding slenderness where I take into account both the yield effect and the ultimate polar buckling effect gives me a resulting slenderness ratio. So that is for a hand these standards are built for hand calculation and not necessarily for FEA analysis with a certain where you need to do all the number crunches to calculate the buckling risk effects. These formulas are based on, okay, suppose I do everything with a hand calculation. I can now see, okay, I can see without doing a recalculation, if I have a certain section where my maximum stress in my top or bottom plate is a certain value, I can use this curve to directly determine what is my maximum effective width, and what is the if I have a if I need to add here a stiffener, what is my maximum slenderness ratio for my stiffener plus plate? Yeah, because if I have here stiffener, the stiffener can buckle. If I have a constant compression stress here, then my stiffener plus plate together can buckle as well. So if I calculate for my stiffener plus my plate together, if I make there an hand calculation, I can use directly, okay, instead of calculating the buckling risk, I can calculate the maximum slenderness I have. And the slenderness is then the beam plus the plate. So that is then this one. I can here determine the A, which is, that's the area of this section, and the I, which is the resistance, the moment of inertia of the plate plus the stiffener together. And then I can determine for that the length, the buckling length, so that is the length between the sections. This is some effect from my students. What is the effective moment of duration? Just to get a quick hand calculation. So if you have the average material is here the end. So if my web is infinitely thin, so I keep the plates separate, then my effective radius of duration, that is this. If I have a square, so a full solid block, then my radius of duration is around 30%, so 28.9 compared to the height. And if I take a circle, then it is as exactly a quarter of the height. For my students, I made a very simple Excel sheet where I calculate the area of my plate, where the limit is maximum the effective width, which we calculated before. So that is maximum 56 times the thickness for S235 or S355, that is then 46. Yeah. The thickness, then the stiffener type, and then depending on the maximum allowable lambda, which comes from this curve, I can directly see what the distance between my sections need to be. Yeah, so with these buckling risk estimation, this course estimation, and simple curves like this one, where I think that the easier approach of grain standards, they use straight lines, but if you do the Eurocode, you can find the same trick. You can quickly estimate, okay, how should I design these things? Yeah. So if we take a summation if we go back to the beam buckling analysis, we have basically a combination of beam buckling and local plate buckling. Yeah, so the global beam buckling is depending on the total length, and the local plate buckling is determined by the width to thickness ratio at the different locations in my section. So how does that work? This is the lattice structure. So this is for free edges again, and for if we compare that value to the limit you have in Eurocode, basically you have the same idea. You have a classification for the full section depending in different classes, where a class 1 is that you have a plastic hinge with full rotation capacity. So basically the whole section can become plastic and then it still is stable. 2 is plastic hinge with some rotational capacity left, so you can not calculate all the way up to the plastic limit for a beam, so the plastic moment of inertia, but almost. And class 3, that is that at least, okay, you can reach the yield stress in your beam because the beam yields before it buckles, local buckling. And class 4, that is also the reason why class 4 is excluded for a lot of different structures, because class 4 means that your shape buckles before it reaches the yield limit. And if we can compare what we just figured out in the calculation, then we see that we came up with a yield limit. If we suppose that yield and buckling are at the same limit, then the width divided by the thickness is 18 times, and the Eurocode is basically the same for constant pressure, only somewhat lower, 14. Yeah, and they take into account the difference in material in a slightly different way. So this is from 80 to 15, so that is 3, that is 1/6 lower. If you take here into account the Eurocode, basically you have the same. So for S235, we take this E as a 1, so then it's 14. If I have 355, this 1 becomes 0.81, so that the C divided by T needs to be at 14 times 0.81, so that is let's say 25% lower. That is then how much is that? No, I don't want to. So that is, let's say, what, 1/6, 25%, something like that. That is quite similar. And so 0.8 times 14, that is minus almost 3. So then you have here 14 and here around 11. Yeah, so although the Euler, the Eurocode takes into account also the effect if you do not have a constant compression but some kind of stress variation over the beam or over the flange itself, the idea is the same. That's only slightly more complicated, because you want to take into account also the effect of a stress, which is the maximum at the end of yield, but at the connection with the web, the stresses can be already somewhat lower. Yeah, but the idea of the classification is to avoid plate buckling. Yeah, and then if we take into account the internal classification of the internal of all the web plates, so to speak, then we see that we have, instead of a limit of 56, they have a limit of 42, and they take into account also the stress variation. So if this one is 1, then this one is 0.67 plus 3, that's exactly 1. So then we have 42 compared to 56. Yeah, but besides that, that is the same. And we also have this E, which is this in the same way. So if we use a higher yield, you need to reach then the classification limit becomes stricter. Yeah, and how do we take into account the imperfection? The Eurocode takes that into account by looking at how it's manufactured. And so we have different buckling curves which looks like this Euler. Where's that curve? Here. So we have here different curves, so up till a slenderness of here in this case, so here we have the yield limit, which is important. So we have a reduction factor, and depending on the tolerance in fabrications, I use different curves. So, and then we go back to these different curves. So depending on whether it is cold formed or hot finished, I have different reduction factor, because that basically has to do with the tolerance, how I can build it. And you can also see that for higher grade steels, the impact of the tolerance is relatively small. Yeah, so but the idea here of the Euler buckling, so the beam checks in Eurocode are a combination of buckling risk, and so the global buckling for the beam, and the plate buckling, which determines the classification. And then we also have for the beam, for the classification, we use these curves. So the thickness to width ratio for the flanges and the web for classification, and we use for the beam buckling risk, we use this combination depending on the tolerances, and instead of calculating the effect of this tolerance, we directly, or the extra moment because of that, we just take into account a general tolerance, which depends on how you produce your section. Yeah, so this is basically it. So we have beam buckling, which is basically a combination of the beam buckling and the internal plate buckling of a beam, and we have plate buckling, where we take into account plate stress in the different directions, but basically we use the same formulas as the ones I presented over here.